Yeah, it started.
Hi everyone, welcome to IISc Theory Seminar. We are excited to have Dr. Jatin Batra today as our speaker for the talk titled Min Sum Set Cover and Tail Bounds for Sums of Bernoullis. He is a reader at School of Technology and Computer Science at TIFR. Prior to this, he was an assistant professor at IIIT Delhi, and prior to that, he did his postdoc from CWI Amsterdam. His doctoral thesis done at IIT Delhi has been awarded Asia Doctoral Dissertation Award. His research focuses broadly on approximation algorithms, and his work has been published in top conferences like SODA and Fox. With this, I hand over to him.
Thank you for the really nice introduction. In today's talk, I will speak about these two problems in approximation algorithms. These are basically generalizations of set cover. So all of you have seen set cover somewhere, right? But here we're looking at a setting when the elements of the sets are being scheduled over time. So typically we think of picking elements in one shot or picking sets in one shot. But min sum set cover is a version where the sets or elements are scheduled over time, and so I'll reduce the problem in a few minutes. So this joint work with Nikhil Bansal, Majid Farhadi, and Prasad Titali. This happened while I was a postdoc at CWI. So let's dive right in. So here's the setting of generalized min sum set cover. So this is a problem that was introduced by Azar, Kamzu, and Yin in 2009. So here you're given a bunch of vertices and some hyperedges of these vertices. And every hyperedge has a covering requirement, which is some integer. And the goal is to order the vertices to minimize the total cover time of the edges. Okay. So think of every vertex is occupying one time unit. Okay. So an edge is covered when any key vertices in it are first selected. So let's see an example. So let's say you have 5 vertices, and I order the vertices as 1, 3, 4, 2, 5. Okay. And let's say my hyperedges are E1, E2, and E3. So first hyperedge is 1, 2, 3. Second one is 2 and 4. And third is 3, 4, 5. Okay. Now let's say, okay, sorry, I think this is moving on its own. Let me fix this. Okay, let's try again. Okay. So here is how it looks like. You have this is the ordering of vertices. And now let us see when every edge is covered. So here all the covering requirements are exactly 2. So when is the first edge covered? The first edge is covered when the vertex 3 has been scheduled, right? Because when vertex 3 is scheduled, then 1 and 3 have been scheduled. So the cover time of the first edge is 2. Okay. How about the second edge? Well, this has exactly 2 vertices, and when are they scheduled? They're both scheduled at time 4. So that's cover time of the second edge. What about the third edge? So there are 3 vertices here, and when are the first 2 of them scheduled? So 2 of them have been scheduled at time 3, as you can see. So the cover time here is 3, and and the objective function here is 2 plus 4 plus 3. Okay, so we sum up the cover times over all the edges.
Hey, Jatin, quick question. So even if KE is 1 for all the edges, how do you capture standard set cover, since you're not looking at maximum cover time but total cover time?
Yeah, great. So I first a bit. So the real general setting is the LP norm of cover times. So if P is infinity, then that's set cover, and Yeah, so sum is the p equal to 1 case.
Got it. Okay, so the L infinity version would with KE1 is standard
Exactly.
set.
Yeah, exactly.
Okay.
Yeah. So I'll talk about that also. Yeah, that most general thing.
Yeah.
Any other questions about this setting? That's good. Okay, looks like no questions. Just a little bit of applications. So Azar comes here and again introduces this problem by giving applications to diversifying query results. Right? So when you search on Google, you search for some query, the query would have multiple interpretations. And you want to see search results for every possible interpretation, and that somehow can be thought of as this generalized min sum set cover. And it also has other applications in broadcast scheduling and many other things. Okay, so yeah, so let's talk about a very special case when all the covering requirements are exactly 1. So this is called min sum set cover. And here, as you can imagine, the most natural algorithm is greedy. Like, you know, for set cover, we use a greedy algorithm, and why not do the same thing here? And indeed, we repeatedly select the vertex, which covers the maximum number of edges. So how well does this algorithm do? Feige, Lovas, and Titali showed in 2004, and also earlier in a more complicated analysis, Barnoulli, Bellar, Haldorson, Shashnai, and Tamir, that this simple greedy algorithm is a 4 approximation for k equal to 1. So remember that set cover greedy is log n, but here you can do better because of this sum objective. And indeed, this score is actually tight. So Feige, Lovas, Titali also showed that unless p equal to np, you cannot get 4 minus epsilon for any non-zero epsilon. Another interesting case is when ke equals the edge size. So here you have to pick every single vertex in the edge before you can call the edges covered. So this is also called as min latency set cover for some reason. And it turns out that this special case is equivalent under approximation preservation to minimizing weighted completion time with precedence constraints. Okay, so here you have a bunch of jobs, and then you have a DAG which specifies its constraints about which job requires some other job to be done. And then, subject to these constraints, your goal is to minimize the weighted completion time. So every job has a weight, and you look at when it finishes, to multiply them by the weights and add it up. So that is standard notion of weighted completion time. And using this reduction, this equivalence, you can actually get a 2 approximation for this min latency set cover. And there were lots of different results by Horst, Schulz, Zwaan, Chakuri, Motwani, Marco, Query, and Wang, and many others. So indeed, yeah, go on.
Yeah, Jatin, let me ask, bother you with another question. So the previous case when KE was 1, the two extremes are the sort of cover time for which you said there's a 4 approximation, and the L infinity is log n. Are intermediate norms also studied there, even for that special case?
Yes, yeah, intermediate norms are also studied, yeah, and I will go to that also. Yeah.
Okay.
Yeah.
So one question, another question. So it is all unweighted case. Are there any weighted version as well where the sets also have weights?
Yeah, that's a good question. So I believe that you can simulate the weighted version by unweighted in some sense by making multiple copies of the sets. And yeah, so I mean, might be that is pseudo polynomial time, but you can do a little bit of trickery to make it polynomial.
Okay. Thanks.
Okay, great. Yeah, so like we have seen for covering requirements exactly 1, greedy is 4 approximation, and covering requirements equal to the edge size, the same as the scheduling problem of weighted completion time with precedence constraints, and we get 2 because of many algorithms for this problem. But now the interesting setting is the most general case when we covering requirements could be arbitrary. So anywhere between 1 and the x size. So here Azar Kamsler and King showed a log approximation, so log of the maximum coverage requirement. And then Bansal, Gupta and Krishnaswamy gave the first constant. So the constant was 485, and this was improved in a series of works by Scotella Williamson to 28, and then by Im, Sviridenko and von der Zwaan to 12.4. Okay. So as you can see, very unlike the other cases where we had these small tight constants, here it has been quite hard to get anywhere close to tight because the only lower bound we have for this most general setting is 4. Okay. 4 is for the min-sum set cover, k equals 1 case. Okay, so this is where we improve. So we show a 4.642 approximation, so we come very close to this lower bound. And here's our technique. So we give a new framework for randomized rounding. So all the other previous works were also randomized rounding, but we show how to make them systematic and view them in one light. And we call our method as kernel randomized rounding. And I'll talk about this kernel later. And as a bonus, we also get a new LP-based Fourier approximation for min-sum set cover. So recall that Feige already showed that greedy algorithm is Fourier approximation, but their analysis is combinatorial. So it does not say anything about the linear program. So we showed the first linear program-based Fourier approximation for min-sum set cover. Okay. So, any questions about these results or? Okay. So another interesting case is that the hypergraph is actually a graph. Okay. So here, all the hyperedges have size exactly 2, and indeed all the covering requirements are exactly 1. So here, Feige, Lovaas, and Detali showed a true approximation. And then this was actually improved by Barenholz, Feige, and Peleg to 1.99946. So that's under 2. But the question is whether we can get significantly better than 2. And indeed, we show using the same framework that we can get 16 by 9. And 16 by 9 is not some random factor. This is actually the integrality cap of the natural LP for min-sum set cover.
So one question, what is the hardness known for this problem?
So so we know that that this is EPX hard, so you will not get a PITAS. But other than that, yeah, we don't know. Okay, so in the rest of this talk, I will tell you this randomized rounding framework using kernels, and I'll tell you a Fourier approximation for min-sum set cover using the LP, and I sketched this 4.642 approximation for generalized min-sum set cover, and I'll also address the other stuff which people have asked about LP norms. Yeah, that's not the main contribution, so I won't list it here, but I'll talk about it as well. Okay, so let's talk about the randomized rounding framework. So first of all, let's think of a very naive independent rounding, and let's see how it fails. So recall right now we're talking about min-sum set cover. So here all the covering requirements are exactly 1. So let's say I have a fractional schedule. So what is a fractional schedule? It's really an assignment of vertices to time slots, but the assignment could be fractional. So you could assign maybe 0.2 of a vertex to a time slot. And now our goal is to round this to an integral schedule. So let's see how we might do that. So let's think that that an edge E is covered by the fractional schedule. For the total extent of vertices scheduled from this edge is at least 1. Okay, so let's say this is our notion of coverage by fractional schedules. Here's an example which is difficult to round independently. Suppose I have an edge with just two vertices, 1 and 2. Okay, and let's say this is my fractional schedule. So I schedule both the vertices to an extent of half in the first two slots. Okay, so half of the first vertex goes in the first slot, half the second vertex goes in the second slot. And the remaining vertices go somewhere much later in future, I don't know. And now let's see what would happen if I round this independently. So first of all, notice that at time 2, this edge is covered fractionally, right? Because half from the first vertex, half from the second vertex. So at time 2, I have covered this edge to extent of 1. But now let's see what independent rounding would do. Well, it would just schedule vertex 1 in first slot with probability half, and vertex 2 in second slot with probability half independently. So with probability 1/4, I will not schedule both the vertices, right? And so with probability 1/4, this edge is essentially uncovered. And so you're effectively incurring an infinite cost with the probability 1/4, and so this is arbitrarily bad. Yeah. Any questions about this? So this kind of motivates what we're going to do. So let's see. So the idea is to first modify the solution using a transformation, and this transformation we will call as a kernel. So we will just multiply this on the left by a matrix, which labeled as K, or the kernel, and we get a new solution called Z. And this matrix can be dependent on the problem. So we will use slightly different kernels, but they all look very similar for different problems. So for min sum set cover, that's when all the covering requirements are 1. And generalized min sum set cover, when covering requirements are arbitrary, we will use some kernel like this. So let's interpret what this is saying. So it's saying that to find the load of this vertex at time t in the solution Z, you take the average load up to time t in the solution X. So that's the sum of the x, v, t prime values for t prime at most t divided by t. So that's average load up to time t multiplied by some constant beta. Think of beta as some small number like 2 or 4 or something. Okay. So like this Green statement says, ZVT is just beta times the average amount of V up to time t. So we're kind of smearing V, so we're smoothing V out, smoothing X out in some sense.
Hey, Jatin, so is it obvious that this will be a feasible solution? Like even if you start with X as, let's say in terms, or you don't really want Z to be a schedule per se. There's no time element.
Okay, I'm not sure what you mean, but here it's possible that so Z may not be a fractional assignment.
Yes, yeah, that's the question.
Yeah, it might not be actually. Yeah.
Okay.
Yeah. So I can talk about it also. Yeah. Good question. Yeah, great point. Yeah. So like he's saying, Z might not be an assignment anymore. X was an assignment, but yeah, about Z you can't say that. But Z will be kind of close to an assignment in some way. I mean, you don't want it to be completely crazy. So
right.
Yeah. Good. Okay, so now let's talk a little bit about this kernel. So first thing to realize is that suppose some LP solution schedules some vertex V to some tiny extent epsilon. So remember that in our example, epsilon was half. So scheduling the vertices to extent half. Epsilon can be now anything, any very small extent, maybe 0.01 or anything. Now you want that Z should schedule the vertex to extent 1 eventually. So that's how you get around that problem with independent rounding. So even though x schedules vertex to extent of half and might eventually cause the rounding to fail, z will schedule the vertex to extent of 1 eventually. So, and that's why it will work. So let's see how. So recall this expression for z, right? Beta times the average up to time t. And let's see what this looks like for this particular x. So let's say my x solution schedules vertex v to extent of epsilon in the first slot. Epsilon is some tiny number and 0 everywhere else. Now what does z look like? So remember z is just the average. So in time slot 1, z is just epsilon, it's equal to x. In time slot 2 is the average up to time 2, so that's epsilon over 2. In time slot 3 it is average up to time 3, it's epsilon over 3 and so on. So zbt is beta times epsilon over t, and yeah, this figure beta equal to 1 for simplicity. So yeah, so z looks like this harmonic series, right? And you know that the harmonic sum diverges. In particular, the total extent of v in the z solution up to time t looks something like beta epsilon times log t, and that diverges. So eventually it will become 1. Okay. So that's kind of why its kernel is good. So any questions about this? Because this is kind of the intuition about what's going on. So essentially, it's making the total load up to time t as log t times whatever x was doing.
Any particular reason for calling it the kernel, or it's just a...
Not really. So the kernel word comes from this machine learning place where you have this transformations called kernels. Yeah.
Right.
No,
Even parameterized algorithm has like a technique, but so it's not like I shouldn't try to connect it to that.
No, think of it more like the machine learning way. Yeah.
Okay.
So where you take the point to some other space. So it's more like that. Taking some x space to z space.
And beta is a fixed constant that you'll reveal later.
Yeah. Beta you just handing in here later. Yeah.
So,
okay.
So another question: so why do you choose this particular type of kernel? I mean, as you see in this kind of, you have harmonic series, but you can possibly have some like 1 plus half plus 1 by 2 square and so on. Those kind of. So what is the reason to choose this kind of functions?
Yeah, it's a great question actually. In fact, for vertex cover, we will do what you said. So we so this for set cover. When hyperedges have size more than 2 potentially, for vertex cover we will use something close to what you said. So we use something like 1 over t cube. And the reason why we choose this kernel is really guided by the problem. So for set cover, what's going on is that the IP solution might schedule the vertex to a very tiny extent. So in fact, maybe you have a set S of size 1000. Maybe every vertex is scheduled to extent of 0.001. And so since the extents are really tiny, if you want them to become big, you have to use this kernel which decays slowly. So in particular here, it decays so slowly that it diverges. But let's say you vertex cover, and there the LP must schedule one of the 2 vertices to extent of half. Because you have to cover the edge, you have just 2 vertices. So this LP will definitely pick some vertex to extent of half. You can use this more aggressive kernel which decays faster. Yeah, and then we do what you said, this 1 over t square, 1 over t cube kind of decay.
Thanks.
Okay. Now let's also address what maybe Arindam had said earlier, that Z may not be an assignment. I'm just multiplying it by some matrix, right? I have no idea what it looks like now. So in particular, if all you want to do is schedule that, if all you want to do is ensure that Z schedules vertex to extent of 1, this is completely trivial. You could just schedule every vertex to extent of 1 in the first slot, right? This is also useless. So you also want that if I pick a slot anytime, then the total amount of vertices should be small. So remember, in X, which is an assignment, every slot has just one vertex, right? So the load of the solution, load of an assignment is exactly 1. But here we are going away from that. But we still want to keep this load to be small. In particular, you can show that if I use the kernel which I just showed you, then the load is at most beta. So in particular, pick any slot T and look at the total extent of all the vertices in this slot. That's going to be at most beta. Beta is some small constant. So Z is very close to an assignment. So that's why this kernel is so special, because it is achieving 2 aims in one shot. It is keeping the load small, and so it is close to an assignment. And like in the previous slide, it is still making every vertex go to 1, because it has this divergent behavior. And that's kind of why this kernel works morally. Any more questions about the kernel?
The covering cost under Z is actually improved over X, or at least as good.
Yes. So they will cover things faster, but it will also incur this extra.
Yeah. So Z by beta would be a genuine.
Yeah. Z by beta is a true assignment. Yes. Okay. So now let's see how you will round this solution Z. So this is something which comes from previous work, something called alpha point rounding. And some of you might not know, so here is what it looks like. So for every vertex V independently, we will pick a slot. And how we will pick the slot? So I will think of ZVT as a distribution over slots T. So for any fixed vertex V, Z is kind of a distribution over slots. Now it's not really a distribution because the sum is not 1 over slots, but we just truncate it wherever it becomes more than 1. Okay, so let's say this area is 1, and I will truncate Z after this. Then I will sample the slot from this distribution, which comes up. The second thing is that in the same slot, you might now have multiple vertices, because I'm scheduling every vertex independently, right? So if you're unlucky, same slot, many vertices might land, but then you just do a tie breaking, and it will turn out that the expected number of vertices in any slot will be at most the load of Z. So this is at most beta, and so this is a small number, and that's really the trade-off. As you increase the load, you end up having more vertices in the same slot, but things get also covered faster. But you can trade off this beta so that your cost is optimized. Okay, so this is how we round Z. We choose a slot independently for every vertex, and then for vertices in the same slot, we break ties randomly.
Hey, Jatin, so maybe this is sort of a digression, but this is morally better than like looking at Z by beta as in a fractional assignment and like, say applying something like Birkhoff von Neumann, or like looking at the convex combination of assignments that generates it and picking one among them. Like, I'm just wondering if that's not a.
That's a good point actually. So what you're suggesting is that so think of zero beta as an assignment, then we'll look at the polytope.
Right.
And we try to find some solution which is good. So we decompose it into multiple integral solutions.
Right.
Pick something good by, I don't know, maximum entropy rounding, some kind of rounding you do.
Yes.
That's a great question. Actually, we also tried that.
Okay.
Yeah, but somehow this seems to work better. I don't fully understand why this seems to work better. Yeah. So one thing is that you really want that for any edge. I kind of want every vertex to have an independent chance of covering that edge.
Right.
And this kind of has a property that for every vertex I'm independently picking a slot.
Okay.
Yeah. So that's one thing maybe. And but also even in general, doing this is better than just working with Z over beta. So yeah. So it's kind of hard to explain why that is, but yeah, but it is true. So if you work with Z over beta, it's not going to work. You really have to work with Z and then
sure.
do that.
Yeah. No, yeah, like makes sense. Yeah, whatever works, I guess, at the end of the day.
Okay, good. So yeah, so literature this is called the intermediate schedule, and then after tie break it's called the final schedule. And this method is called alpha point rounding. It kind of seen many works on scheduling. So here's a summary of what we just said. So we first solve a suitable arbitrary relaxation to obtain a fractional schedule X, and then we apply the linear transformation on a kernel and get a new solution Z, which may not be a fractional schedule anymore. And then we do alpha point rounding and get an intermediate schedule. And then we break ties at random and get the final schedule. And like I said earlier, for different problems, we have different kernels. So for Minson set cover and generalized Minson set cover, our kernel look like this, beta times the average load up to time t. But for Minson vertex cover, we use this 1 over t cube kind of kernel. So some constant times 1 over t cube, and then instead of adding up the xvt primes, we multiply them by t prime square. This ends up being the right thing to do. The reason is what I kind of said earlier, that in vertex cover, the LP must schedule every vertex, one vertex of every edge to the extent of at least half. So you don't need a divergent kernel. And if you use this new kernel for Minson vertex cover, then the load will be smaller, and that, like I said earlier, it helps. It helps to so in the alpha point rounding phase, the number of vertices in one slot depends on the load. So low load will help the rounding. Okay, so now we get a bit technical. How much time do we have? Yeah, still have time. So let's talk about this Fourier approximation for Minson set cover. So right now we are in a very vanilla setting. All the common requirements are exactly 1. And now let's see how we can analyze this for Minson set cover. So let's just recall what the LP is. So we have some variable xvt for whether vertex p is scheduled in time slot t. And let's say I have a variable yet for whether some edge is covered in time slot t. And then the cover time looks like some overall t of t times yet. And then you can write some natural constraints. So yeah, I won't bore you with them. And what is the analysis idea? So for every edge e, we analyze in 2 steps. So first of all, we have an intermediate schedule, and we lose the factor of beta over beta minus 1. And then we break ties at random. Then we lose this beta. And this beta happens because the load of the solution is beta. The load of Z is beta. That's why you lose beta in the second step. The total loss is beta squared over beta minus 1, the product of these 2 losses. Then you optimize this, and you get beta equals 2, giving approximation ratio of 4. Yeah, so that's the plan of the analysis. The second step, as I said, is just because of the load being 2, being beta, So let me talk about the first step, about the intermediate schedule. So here we use somewhat unusual technique of using a non-linear convex program. So let me build to that. So first just some preliminaries. So the expected cover time of an edge can be thought of as just adding up the probabilities that the cover time is at least some time t. So let the PET be the probability that cover time is at least t, and I just add up PET over all time times t. That's my expected cost for any given edge. And now, since every vertex is scheduled independently, I can write some expression for this probability in terms of every vertex, wherever every vertex is scheduled. And I can do a little bit of algebra and get some expression. So don't worry about how the algebra happens. But the upshot is that I will get some expression for this probability. The probability that the edge is uncovered at time t. And this expression turns out to be something like this. It's exponential in the LP variables. So I have the LP variable y, and I have exponential of some linear function of the LP variables. So now that we have this, how can we find an approximation ratio? How can we analyze this? So we have this linear function with an exponential, and now my LP cost is some linear function again, right? So I have to bound the ratio of this exponential of a linear versus a linear. And so now think of this as an optimization problem in these LP variables. So let's call the LP variable as some new formal variable, AT. And now all I have is this optimization problem. The numerator corresponds to the cost of my algorithm. It's wrapped bound on my cost. The denominator is the LP objective. And I'm asking, what setting of the LP variable would give me the worst possible approximation ratio? So this kind of technique has appeared before. So if some of you are aware of what is called a factor revealing LP, you might have seen it in context of facility location, and maybe also some other problems in online scheduling. But here we have this factor revealing nonlinear convex program. Although this is not really convex, but this is the ratio of a convex function and a linear function. So we can think of this as almost a convex program. We can use our properties of an objective. In particular, we can use the fact that such a program has optimum at a vertex of the polytope. And then using the vertex properties, you can show that you can find the exact worst ratio. So any questions about this idea of using this nonlinear convex program to find the ratio? So notice that we're not actually going to solve this program anywhere. This is all for analysis. So we'll be trying to find the worst possible setting of our LP variables, which will maximize the approximation ratio of our algorithm. So we're looking at the ratio of the algorithm's cost and the LP cost, and that luckily turns out to be this ratio of a convex function and a linear function.
And you want to show that this ratio is upper bounded by beta over beta minus 1.
Yes, exactly. Okay. And that you can show by an explicit calculation.
Okay.
Because optimum is at a vertex, so you can figure out what a vertex looks like. From that, you can just work it out.
So, and like it also tells that for certain instances you are doing better. Like that's a worst case overall possible. I guess
Yes.
So the CT T primes are instance dependent, like they depend on the. So this probably also tells you that like you are not solving it, but sort of an interesting sort of side note would be that I can, like, given an instance, I can sort of solve it and say, oh, by the way, for this instance, the approximation ratio is like slightly better.
Yeah, indeed.
Yeah.
Definitely.
Okay.
Yeah. Good. Okay. Okay. The rest of the talk, I want to sketch this. A real result, which is this improved approximation for generalized Mills and set cover. And here we also talk about this tail bound for sums of Bernoullis, which you might have seen in the abstract of this talk. So here's a very rough outline for this. Yeah, I can't go into details, but this is the main idea. So first of all, if I use a natural LP for more general problem of arbitrary coupling requirements, then that has an unbounded integrality gap. And this kind of happens for the same reason that knapsack type problems have unbounded integrality gap. And we strengthen this LP by using what are called knapsack cover inequalities. So these are very interesting and simple inequalities. They have found lots of applications in many problems. I encourage you to look them up. And once you have this, once you add these knapsack cover inequalities, then the rest of the analysis is very similar to Mills and set cover. So let's just see what it looks like. So again, we're looking at the probability that a given edge is not covered at a given time. So PET is that probability. But now the edge is covering requirement KE, which is more than 1. So now the edge is uncovered if at most K minus 1 vertices have been scheduled by time t. And that's the bad case. So, to upper bound this, let's make a Bernoulli variable xvt, which captures whether the vertex is scheduled by time t, by our rounding. And let's look at the sum of all vertices in the edge of xvt. Okay, so now this bad case, when the edge is not scheduled by time t, is exactly when st is at most k minus 1. Okay, so the sum of these Bernoulli variables is strictly less than the covering requirement of the edge. So now let's see how this looks like. So let's look at the expectation of this st. So fix the time t, and let's look at the expected number of vertices from the edge which you have seen so far, which have been scheduled so far. Now, this expectation itself is less than the covering requirement, then there's not much hope, right? Because K can be very large. The probability that the real ST which you sample will be at most K minus 1 will be pretty high. But you can hope if this expectation is at least K. And so interesting thing will be to look at, so we want to upper bound this probability that ST is strictly less than K as a function of this ratio, as a function of the expectation of this sum divided by K. Let's call this number as gamma t. So we only look interested in the case when gamma t is at least 1. So looking at the case when expectation of ST, so expected number of vertices scheduled so far is at least the covering requirement. And now you want to see how good a bound you can get on the probability that the edge is not covered. The probability that the number of vertices actually scheduled by time t is strictly less than K.
So this is slightly complementary to like a Markov inequality. You actually want less than KE in terms of that ratio.
Yeah, exactly.
Okay.
Yeah, so Markov goes the other way around. This is
right. Okay, that's interesting.
Right. And so you want to leverage some sort of concentration properties of this because you're summing up these over these Bernoullis. Right. So yeah, so that's what we're going to talk about. So now let's just talk about sums of Bernoullis. So even if you don't understand anything so far, you can start afresh in this slide. So you have a bunch of independent Bernoullis. Let's call them xi's, and I'm interested in their sum of xi's. I tell you that the expectation of the sum is gamma times k, where k is an integer and gamma is some constant which is at least 1. So expectation is definitely at least k. How much more than k? That depends on gamma. And now my question is, what is the best upper bound we can get on probability that S is strictly less than k? S is at most k minus 1 as a function of gamma. Okay, so you want an upper bound which is independent of k, depends only on gamma. So yeah, I'll give you a minute to digest this. So what's your guess? Like, what do you guys think should be done here?
Why are you calling the upper bound p as a function of gamma? You want a
So we want that that as gamma becomes bigger, this probability should become smaller.
So what does the expression p of gamma mean here?
Let's look at. Okay.
Oh, that's not probability. There's just some function of gamma. Okay. Okay.
Yeah.
Okay.
So looking at the supremum of this probability over all k and all possible xi's. So xi's are independent Bernoullis, but they could have any distribution. They may not be identical.
Right.
So yeah. This is supremum of this probability over all possible Bernoullis whose sum is gamma k, and it's supremum over all k in fact.
Right. And in the best case scenario, like, okay, you would have identical Bernoullis, which would be like an exponential decay. You're hoping something similar happens.
Yeah, so actually, even if you have identical Bernoullis, it's not obvious that your decay will be exponential. So, so if gamma, so if k was exactly 1,
right,
then your answer is e to the minus gamma.
Right.
But if k is large, then it's not so clear anymore.
Okay, I see.
So that's really the open question. So okay, so let's throw what we know at it, right? All of us know Chernoff. So
Jatin, like very close to k, something like anti-concentration would tell you that it won't fall very quickly, right?
Yeah. So so indeed, we're looking at a regime when this deviation is very small. So so expectation is gamma k, and S is at most k minus 1, and gamma is really close to 1.
Right.
So this deviation is pretty small. So looking at this very fine bound.
Right.
Yeah. So indeed, if I just throw what I know, if I just throw Chernoff at it, then I get P of gamma to be roughly e to the minus gamma, and this is actually tight for k equal to 1. But this is true only for large gamma. But if gamma was close to 1, then Chernoff will give you a trivial bound of 1, because exactly like what Arindam said, if k is if gamma is almost 1, and deviation is really small, and then anti-concentration, so the counterpart of Chernoff, the lower bound for Chernoff, will give you that. You can't do much here. And for Chernoff itself will give you only a bound of 1. However, Jyotio and Samuel showed that if gamma is exactly 1, so the expectation of S is exactly k, then the probability that S is at most k minus 1 is in fact at most a half. So indeed half is tight for as k tends to infinity. So indeed, if gamma is 1, then the right answer is actually a half. And that kind of improves Chernoff. Chernoff will give you just 1 here if gamma is 1 for large k. But the right answer is really a half. Okay, so our question is that what is the right dependence as gamma is more than 1, but gamma is small. So gamma is large, then like I said, Chernoff will give you the right answer. Chernoff will give you t minus gamma. But what's the decay when gamma is almost 1? So we show that for all gamma at least a 1, this probability is at most e to the minus gamma times this factor, which is e over 2 to the e to the 1 minus gamma. So let's try to parse this a little bit. So if I plug gamma equal to 1 in this bound, then you can check that I will get a half. So gamma equal to 1 matches the right bound of Jogio and Samuels. And as gamma becomes large, this decays like Chernoff. It decays like e to the minus gamma. So the intermediate regime, when gamma is more than 1 but still small, we are saying that this bound goes like e to the minus gamma times this factor, which is e over 2 to the e to the 1 minus gamma. Any comments on this bound or this setup? Plenty of time, almost done.
Yeah, so and the proof here is like again exponential Markov, or do you like is it something different?
Okay, actually that is a bit surprising. So the proof goes like this. So we use this Jogio-Samuels result as a black box. So Jogio-Samuels prove that if gamma is equal to 1, so if you're looking at exactly k versus k minus 1, then your answer is exactly a half. So we use that as a black box. Then we use a kind of monotonicity. So as gamma increases, we show that our life only gets better in some sense.
Oh, okay.
Yeah, so we kind of do induction on gamma. Okay, not induction, but so we make an expression in terms of gamma. We show that this expression only gets better as gamma increases. So yeah, so we do calculus.
Oh, interesting. And this is tied to Bernoulli because this the result that you're stating of Jogio and Samuels is also for Bernoullis.
Yes, all of this is for Bernoullis. They don't have to be identical, but they do have to be independent.
Okay. So things like negatively associated and so on, which works for say Chernoff, might not work here.
It's a great question. I have not checked it, but yeah. But, I mean, if you look at Jogio-Samuels carefully, I'm not sure. So the thing is this. So let me just say one more thing. So we crucially use the fact for this proof that the worst case is the Poisson regime. So if your variables were negatively correlated, then I'm not completely sure what you can do there. So we explicitly use the form of the Poisson distribution. But if the variables were negatively correlated, then would you still get some form similar to Poisson?
Yeah, the Poisson approximation actually even works for those. So I mean, while I haven't like, but at least that Poisson approximation for Bernoulli holds even with. Yeah, so it might extend.
It might extend.
Yeah.
It's possible. Yeah. I mean, right now it looks possible that because that's all we are doing. We look at the Poisson limit,
right,
and then we start with Jogio-Samuels, and then we show that okay, life only gets better as gamma increases.
Okay. Yep.
Any other thoughts on this? Yeah, this is almost my last slide. One more slide only. Okay, take your time. Another question is what happens in the upper tail? This is the lower tail, right?
Right.
Upper tail, yeah.
And this is also tight, like you said. Jodot-Samuels is tight, and you think this is also tight.
Okay, so Jodot-Samuels is definitely tight, but ours is probably not. So we did some computer simulations, and we could see that the computer actually gives you a better count than this. So
okay,
this is not. Only if the gamma equal to 1 case is tight, but gamma more than 1, it's not.
Interesting.
Does this extend to k minus r or k minus 2 and so on?
That's a good question. I mean, it might actually, because I don't think anywhere in the technique we have very strictly use the fact that it's k minus 1. I mean, everything that I've seen should extend. The only thing is that you have to see what Jodot-Samuels says for k minus r. Because whatever we do should also work for k minus r. But I do believe that even in Jodot-Samuels, you don't really need k minus 1 specifically. Of course, your bond would change. It would not be half anymore, right? It would be something different. So maybe the function of r you could get something. It's possible. So of course r would have to vary as k, right? Because if r is a constant, then I think it would still be half. Okay, yeah, we can take this offline. But it's a good question. Okay, so yeah, maybe I'll just finish off now. So we just do same thing which we did for Wilson set cover. We again make this convex optimization problem, but now the analysis is much more tricky. But yeah, it requires many pages of calculation. But now it can still be done. And we can also show by numerical experiments that our algorithm is actually better than what we claim. Analysis gives 4.642, but if you do computer simulation, then this convex optimization problem actually has a better solution. It gives you an approximation ratio of 4.523. But if you're hoping that this will get you all the way to 4, that is actually not true. So we have an example which shows that our algorithm has an approximation ratio of at least 4.509. So if you want to get all the way to 4, you need a better idea. So that's it. Yeah, I'll just end with this last thing about LP number of cover times. This is what we are in the mask at the very beginning. So this is the same setting as Wilson set cover, but now you want to minimize the LP number of cover times. So if P is equal to 1, then that's Wilson set cover. If P is infinity, that is set cover, which is a classic thing from approximation algorithms. But interesting thing is what happens if P is between 1 and infinity. So we show that you get a bound of P plus 1 to the 1 plus 1 over P. And this is also the best possible if P is not equal to NP. And indeed, if you plug P equal to 1 in this, then you'll get exactly 4. And you also get log n if you plug the right value of P. So if you plug P to be about log n, then you'll get roughly log n. This tightens the results of Golovin, Gupta, Kumar, and Tan Vuxan. And in fact, we have two algorithms which ostensibly achieve this term. So one is the same randomized routing framework as we had for the other problems. However, here we have a slight issue. I mean, so we can almost show that this works, except for a conjecture which we can't prove. But it looks like this works. Yeah, but we're not completely sure of this. But we do know that greedy, which is oblivious of P. So greedy algorithm is the same as the greedy algorithm for Wilson set cover and set cover. So that algorithm is a simultaneous tight approximation for all P. And interestingly, we give a new analysis for greedy using dual fitting. So particular for the linear program, we can construct a dual solution of sufficiently high value. And this actually mirrors analysis of speed augmentation. If some of you have heard of speed augmentation, how we use dual fitting there, this is inspired from that. So thank you for your attention.